welcome you all here to our 2016 summer star party. At least it feels like that. Great to see you all up here. By show of hands, who's up here for the first time? Outstanding, outstanding. Well, it's great to have you here. Copernic's been around for over 40 years. We are an informal educational institution. Clearly, we do astronomy very well, but we do a wide range of activities for children, literally as young as 3 years old, through high school. But then we also do programs every Friday night that will start up again in March. And of course, if it's clear out, we'll open up our domes and do some observing. So we would love to see you back here, and we also would love to see you become members here. It's part of what helps keep us going. We receive no government support, and so we rely on donations, memberships, and tuition on our classes to keep the doors open. It's really an honor to have great speakers here, and tonight is no exception. Dr. Don Barry is from Cornell University, and he'll be talking about the kind of light that you can't see, but ultimately that still has a lot of interest and a lot of information. So with that, I'm going to turn this over to Dr. Barry.
Thank you, everyone. Let's see how this is. How's that, everyone? Can you hear me? Good. I'll try to talk up a little bit. Thank you very much, Drew. And if we can, there we go. There we have the first slide. So it is really a pleasure to be here to see such a wonderful turnout tonight on a night which is not exactly optimistic, maybe by the standards of Binghamton, Central New York. I live in Ithaca. We have basically the same weather patterns that you do here. It is the cloudiest area of the country. So there are advantages if you live in an area like this to learn other ways of doing astronomy, not just with a telescope in your backyard. I spend most of my time looking at data that comes down from telescopes in space. So it keeps me on a day schedule most of the time. And I don't have to worry about the clouds and the rain because the data is there. And it's always clear in space. So I'm going to tell you a number of things today. The general theme is going to be looking at the universe with eyes other than our own. And I'll try to keep it simple. There are going to be a few technical things that I talk about, but we have astronomers of all ages in here and all levels of expertise, and there's hopefully be something for everybody. So, first of all, let's talk about light. Here is, if I can get this nice bright flashlight. Light from the sun, later from fires, from other sources of artificial light, were what enabled our, I'm not going to call it the primary sense because everybody, I think, has a different primary sense. But certainly one of our most significant senses are our sense of sight, our sense of vision. And this was the only sense by which people could do astronomy for millennia. So using our eye as a telescope of one power with no extra amplification of any type, people did astronomy. The ancient Greeks did astronomy. People even before recorded history did astronomy. We just don't have records of it because there are no records from such a time. And all sorts of things were discovered with the simplest of all telescopes, the eye, without anything else. Simply watching the march of the constellations across the sky as the seasons progress, watching the march of the planets across the fixed stars in the background. And from this, the first models of the universe were constructed. Ptolemy, in the first few centuries AD, he had no telescope. They had not been, it was centuries before telescopes were invented. But he was able to measure the position of the planets and to construct a mathematical model to predict where they would be a month, a year, a century, a millennium from the present. So all without anything other than our built-in Power One telescope. Now, of course, if you're using light as your tool of discovery, you want to understand it. The ancient Greeks did not understand what light was. Ptolemy did not understand what light was. He knew how to use it. The understanding of what it was really required the 20th century, and we still have unanswered questions about the details. In science, we're always digging deeper. It's never ending. We come closer and closer to the truth, but we're never going to get there. It would be very boring to be a physicist if you achieved the truth and it was all done. So, what's a fundamental question that you can ask about light? Is it a pure substance, or can it be decomposed? This was a question that occurred to Isaac Newton. Now, I'm sure that Isaac Newton's a name that just about everybody in here knows, right? Isaac Newton was the first person. It could have been done centuries earlier. He was the first person to take a beam of white light. He used the sun. Let me find a dark corner of the room. Maybe this will work. And he aimed the light at a prism. Well, I don't have a prism here, but I have something that does the same thing. Can you see up on the ceiling what I have here? If I aim it from the other side, it might be brighter. One of these sides is a little brighter than the other. That's the, actually. There we go. What do you see? Rainbow of colors. Do you see a rainbow of colors here? But you see it coming from here. By the way, you can repeat this yourself if you have a CD. Everybody has a CD. And a flashlight. Aim a bright flashlight at a CD, and you'll be able to turn the white light into a rainbow. Yes? That's exactly what they do, and that's what you just saw. That is a device called a diffraction grating. It's not a prism, but it works on a slightly different principle, but it separates the light out. Now, what do you think the next thing that Newton did? He was able to show that white light can be decomposed into all the colors. Well, that would take a long time. It would take centuries to work out the details for that. But that's a really good answer, because that's certainly something you want to understand. The how would have to wait. The next thing that Newton asked was, if we've been able to take white light and convert it into colors, are we separating the light out, or are we introducing some new quality? So he used another prism to put the colors back together. And what do you think he got? White light, showing that it was a separation and not adding a new quality. Everyone with me there? So, astronomers spend a lot of our time figuring out new ways of separating light out and exploring new parts of the light that are even beyond, in fact, far beyond our ability to see with our eyes. So our eye sees only a narrow part of the colors that nature makes available to us. Now, I have a graphic here. You see the rainbow here, red light at one end, violet at the other. If you've learned Roy G. Biv as the color of the rainbows, this is backwards. I apologize. This is a blown-up, magnified section of the spectrum of what's this tiny, tiny little sliver of what we call the electromagnetic spectrum. So nature produces all of these types of, I use light now in the very broad sense. It includes radio waves, as was discovered by Heinrich Hertz in the 1880s. It includes ultraviolet, which gives you a tan on a sunny day, not that we ever have those around here. It includes the X-rays that you use to take pictures of your bones, gamma rays, high-energy things that come from nuclear reactors. And it also, I'm going to spend a lot of time talking about the infrared. So infrared, infra sort of means next to the red, beyond the red. And this was the first type of radiation that was discovered that was not visible light. It was the first extension, the first amendment of the laws of physics beyond the light that we can see with the eye. So the next slide will show how that happened. This is the astronomer William Herschel. What's he best known for? Well, he's actually known for a bunch of things. He was a composer. That was how he made his money for a number of years before he made his fame in astronomy. His music survives. You can buy CDs of it. But in the 1780s, he discovered a new planet, the first new planet ever discovered that had not been known since antiquity, the planet Uranus. And you could well imagine that made him a rock star by the standards of the age. And he became very noted. He was given a pension by the king, King George at the time, the same one who we have some trouble with the colonies over here. And he was a polymath in astronomy. He had no teaching. He was all self-taught, but he made a number of fundamental discoveries. And one thing that occurred to him was Newton has turned white light into a rainbow. But if you saw the rainbow when I projected it here, did it have hard edges? This painting is false. It shows that the blue end there has a hard edge, and that the red end over here has a hard edge. That's not how you see it. It fades out. So is that fade out real, or is it because our eye loses the ability to sense the color? So Herschel did not know, no one knew. So he tried to find some way of seeing beyond the red and beyond the blue at the edges of the rainbow. Is there any way that he could get this to make an impact, a reaction, a change, something physical that could be seen? And he finally succeeded by putting thermometers beyond the red end of the spectrum. Here you see a network of 3 thermometers, one that is where the red light would extend, the temperature went up. The others did not. So he was able to show that there is something there. We can't see it, but there is something there. This was in 1799. He did not find anything at the blue end of the spectrum, but guess what? The instant that he discovered something at the red end, everybody in Europe started looking at the blue end. It took 1 year before ultraviolet was discovered on the other side. Not by Herschel, because as soon as, you would think that it could have been done centuries earlier. That's the thing about science. It always appears obvious in retrospect. Well, sometimes it's really hard to do technically, yes. Pardon? The past is, every moment becomes the past just a second later. If we could sort of go in the future, it would take the fun out of doing science in the present. So, Herschel discovered there's something there. And it would be another 150 years before we would really learn how to do much more than it. People rapidly realize that the warmth that you feel from a flickering fire, it's infrared. That's what the thermometer is registering here. So we can sense it, not with our eyes, but with our sense of temperature perception. When you hold your hands out in front of a nice warm fireplace, you are sensing infrared radiation. Now, you could do that with the stars, but they're not really very warm at this distance, so you won't feel them with your hands, but you are getting infrared radiation from them. So it took a while before we were able to develop instruments that could expand our technical capabilities to the point where we could apply this. So he's doing astronomy here. This is coming from the sun. But it would be nice to be able to do it to other stars as well, and not just be centered here in the solar system. So I don't remember the order of my slides, so I'm going to be making some of this up as I go along. The point here is that every part of the spectrum gives you a new window that you can open and look through at the universe, and things look very different. So there are some things that you can learn with regular light. And as we've opened new and new windows across the spectrum, each one of them tells us something different because the processes that produce the radiation are different across the spectrum. What do you think produces visible light, primarily, in the universe? Stars. And what's a property that stars have? They have lots of properties. Heat. Stars are hot. That's the key thing. And because they're hot, they emit light. So when we look through telescopes with visible light, we are seeing hot things. There are a lot of things in the universe that are hot. There are also a lot of things in the universe that are not hot. And what do they appear like through a telescope? They're dark. We don't see them. So, building instruments that can see, not invisible, but at infrared, lets us see the cold part of the universe. And there's a lot of it out there. These are just pictures across. We have the Milky Way as it appears in visible light. You can see the band of the Milky Way, lots and lots of bright stars. We go up to the infrared, the stars largely go away. And we can still see the band of the Milky Way, and these are clouds full of gas and dust. The dust emits in the infrared, even if it's at the temperature of this room, or colder, even if it's 100 degrees below zero. It emits in the infrared, and we can see it. In the radio, we're also able to see clouds now of gas. Dust doesn't really produce radio. So our ability to see the invisible clouds of hydrogen in the universe, we can see in radio. Everything has a different appearance. When we get down to the really, really high energy parts of the spectrum, X-rays and gamma rays, we have telescopes that produce much sharper images than this. But what we see are things like the center of our galaxy, where all sorts of exotic processes are going on that give rise to energetic radiation. And our X-ray sky, especially, this is a very, very old picture that predates the premier X-ray telescope. It's been up since 1998. Most of the things that we see through an X-ray telescope are neutron stars and black holes that have gas being sucked out of them, the exotic objects, where things get extremely hot and the conditions are at really the limits of what we can understand. And we would not be able to understand these objects if we didn't open the windows into the spectrum. Now, just a little bit of history at Cornell. We've been doing astronomy there for a number of years. This is a picture from 1923 when we commissioned this telescope, which, by the way, I'll make a plug for it. It's open every Friday night during the academic year and a lot of Friday nights otherwise for people to come and look. So we welcome you. Our students run the show. And just like the docents and volunteers here make it possible, our eager students make it possible at Cornell. So this is Cornell's first astronomer, Samuel T. Boothroyd. Really interesting fellow. He grew up in a sod house in Nebraska. And before he got his degree in astronomy, he and two mules traveled along the Canada-U.S. border surveying it in 1898 through 1902. He then went off to the University of Washington, got a PhD, came to Cornell. Back to Cornell, he actually did a bunch of surveying at Cornell earlier. And he started studying. He was one of the first astronomers to look outside of visible light. He looked at ultraviolet. We can't see it with our eyes, but photographic film responds to ultraviolet. So we have a tool that can detect it. And he started building special telescopes and special devices that could work with it. He started trying to understand the property of the very hottest stars. They put out most of their light in the ultraviolet. And to really get a full understanding of it, you have to look in the ultraviolet. Infrared would come a number of years later. Oops, one of my slides is out of order here. In fact, it's not showing it. Let me see why. Hold on a second. There's a problem with the infrared. Let me give the... There's a problem with the infrared. Now, before I talk about what this means, we have an infrared camera here. Most of you have had a chance to look at it. And infrared, as I said, detects heat. Make sure it's safe. I think you'll all agree that we have a little bit of heat coming out here. Infrared can do other things as well. We have here two supposedly identical bottles of water. Yeah, one of them has seen a little bit of time in a microwave not too long ago, the other's from the refrigerator. So you would never be able to tell that their properties were different at a distance unless you had an infrared camera. I can tell that they're different because my hands are on them. And this one's cold and this one's hot, I think. But to the infrared camera, it's obvious. These cameras, by the way, are commercially sold because they can tell you if your house has a bad spot in the insulation and it's leaking heat. It can also be used by soldiers to find someone hidden on a battlefield in the middle of the night. Can't hide body heat. So they have a lot of advantages or disadvantages depending on which side of the battlefield you're on. But they also have other properties. Can you see me? Can you see me? Infrared light can pass through things that ordinary light can't. You can see my hand. But invisible light, you can't. You can kind of see it. You're going to be a good scientist because you're critical. Scientists must always make sure you get the best possible, fullest explanation that's accurate. So infrared can see through some things. We'll get back to that in a little while because it enables us to see certain types of things. But there's one thing that infrared light can't see through. Well, as a matter of fact, first of all, what color are my glasses? It indicates they're cold. Well, they are cold, but even if I warm them up a little bit, why can't you see my skin behind it, behind the glasses? Infrared light does not pass through certain types of plastic. Glass, it depends on the nature of the glass. But whereas infrared can penetrate some things that light can't, there are other things that light gets through that infrared can't. One of the worst offenders, which is really bad from the point of view of astronomers, and infrared astronomers, we really hate it, is that infrared light is blocked by water and water vapor. So this is a graphic that shows as you can see, it's a map of the Earth, and we have here indicated in colors how much water there is in the atmosphere above the sea level. So if I were to take, is there a garbage can here? Oh, there isn't one, but I'll hold my hands out. If I were, thank you, Drew. So let's say we want to figure out how much water there is in the atmosphere. Let's build walls up on top of this garbage can, all the way to the top of Earth's atmosphere. And now let's just sort of wave something and have all the water rain down and figure out how deep it would be in the garbage can. That's how much water there is on top. So if we were to take this room and rain all the water down and have the roof not in the way, well, it's actually not all that much. You can see, well, I don't have the key here, but these heavy areas here turns out to be about 2 inches. Now, of course, if there's storm clouds on top of you, then that's a totally different thing. But just in ordinary dry air, there is still water vapor, and there's a lot of atmosphere. There's about 20 miles worth above us until we run out of atmosphere. And if we rain that water down, in the tropics, where it's really humid, you can get about 2 inches. In dry spots, like unfortunately parts of California right now, you can have considerably less. Some of the driest spots, they're not indicated here, are actually down in Antarctica, and also part of the coast of Chile here. And in those areas, instead of 2 inches, you can get a fraction of a millimeter in really good conditions. And it makes it possible, since this is blocking our view of the infrared sky. The dry areas on the planet make it possible to see what's going on. Go. On mine or on yours? I thought I had turned that off. Okay. Well, if I talk too long on one slide, let me know. So there are 2 words that infrared astronomers are very familiar with: high and dry. If we're going to see the infrared universe, we need to be above this river of humidity. Yes? Well, because in Antarctica it's very cold, and the South Pole is very high. It's 9,000 feet. And the cold temperature of the air keeps very much water vapor from being in the air. Now, it's also very expensive to get to Antarctica, and it's not exactly a pleasant place to live. So, although it is the best place on the planet if you're actually on the surface, it has a lot of disadvantages. Chile, you can actually drive to 17,000 feet in Chile. Even higher, and even though it's not as cold, a lot of the time the atmosphere is really, really dry. So we do a lot from there. There's also the Hawaiian Islands. Well, there may be not too much at sea level, but they have a 14,000-foot peak, and there's a lot of infrared astronomy that's done up there, high and dry. So we're able to do infrared astronomy from the ground. We started building, actually, telescopes at Cornell to test things in infrared in the ground, but starting in the 1960s, we had several astronomers who were hired to really push what infrared could do. So even back in the 1960s, we did not have telescopes at the South Pole. We did not have telescopes at 17,000 feet in Chile. But we did have access to high elevation in another way. We had a team that would actually build small telescopes and put them on rockets. And these would fly up above the atmosphere. They were leftover World War II sounding rockets, or rockets that were developed from a lot of leftover detritus from World War II. And you would have a chance to do astronomy for about 6 minutes. And then the rocket would arc over. Hopefully the parachute would deploy. It didn't always. And it would land, and you would retrieve the magnetic tape recorders, and you would have a chance to point one or two things, two places. And we were able to do astronomy for the first time without any water vapor at all, with the atmosphere completely out of the way because you had gone 80 miles high. And later on, NASA started developing a number of planes that actually had holes cut in them, and small telescopes about the size of the ones in the backyard here could be operated on board a flying observatory. And these would fly up to about 45,000 feet. And there you're above, not all of the atmosphere, but you're above 80% of it. And above 99.99% of the water vapor, because the air up there is very cold and very dry in the stratosphere. So we have a long history at Cornell of doing even better than on the ground, of going to exotic locations high in the atmosphere, and even more exotic, as I'll get to in a few minutes. Now, what can you learn? This will be I think, one of only 2 graphs, so don't freak out that I'm going to go into a whole bunch of it. Remember the spectrum at the top? If we make a graph that shows how much light there is at every color, well, one thing that the spectrum tells us is that 2 things that look the same to the eye are still at different places in the rainbow. The eye only sees 3 colors, red, green, and blue. All the other colors are made by combinations of red, green, and blue. But the spectrum has light of different properties, but it all appears red to us. So if you measure what the intensity of light is and where it is, you can distinguish more colors than the eye can see. Now, I'm sure all of you know how hard it is to match colors when the eye can only see 3 things and you're trying to get the bedroom ceiling to be the right shade next to the walls. Well, imagine in astronomy, we have instruments that can distinguish 500,000 colors. And if we make a plot, a graph, and we plot intensity, sometimes we find that the spectrum has bright or dark zones. And this is wonderful because it turns out that those bright or dark zones are a fingerprint for the physics that's going on for what we're looking at. Now, I'm sure you've read things where astronomers say the star was measured to be at a certain temperature, this gas cloud was measured to be at a certain pressure. Do you think that we went out there and stuck a thermometer in the star? We can't do that. We can do that a few places in the solar system, but the universe at large is far too vast. We have to develop methods of recording physics at a distance. And the spectrograph, which separates light into the colors and makes graphs like this, can do that. So where lines occur is, I'm not going to get into all the details in the physics, but they tell us things like temperature and pressure, and also the composition. So a dark line like this, which makes a little divot in the spectrum, is going to be produced by the interaction of light with a chemical substance. Every chemical substance has a different fingerprint. And just to show you what you can do with this, here's a picture that was made by an amateur astronomer from sketches through his telescope in 1905, Percival Lowell. He was a bit of an inspired crank. Looking at Mars, he started inventing all of these little narrow features, and he saw that Mars had sort of greenish zones in the equator, and he could see that it had ice caps at the poles. And he then invented an entire history for a civilization struggling to survive, building canals to husband the water from the poles, to struggle to grow crops at the equator as the entire planet is dying. And so the question is, how can we figure out if Mars has water on it or not? You can't just do it by seeing what look like canals and areas that look slightly greenish. Well, in 1967, we finally sent a space probe to Mars. A certain Cornell astronomer by the name of Carl Sagan had a lot to do with this. And this picture looks a little different than Percival Lowell's sketch. You don't see the canals. It's black and white, so I'm not going to make any arguments based on color. But it looks sort of dry and desiccated like the moon. So at one fell swoop, not a lot of people believed the idea that Mars was loaded with canals and water coming down from the equators. But when this picture came out, people thought, okay, well, it's totally dry. It looks just like the moon, and 2 years after this picture were taken, we landed on the moon, and we found there's no water there at all. Well, in 1973, my colleague Jim Houck at Cornell, flying in one of those airborne observatories, measured the spectrum of Mars in the infrared. And the same color of infrared light that blocks us from viewing when we're looking through our own atmosphere also absorbs light that strikes Mars and then bounces off. And this divot, this low absorption at a certain color of infrared light, we knew corresponded to water. So this was a measurement that there is water bound in the Martian soil. Not a lot, but some. So without going to Mars, we could tell that there's a little bit of water in the soil. This was 1973. 3 years later, Viking lands on Mars, and it's able to make a measurement right there by digging up some of the soil and using its onboard chemical analysis tools. And it verified this measurement, taken tens of millions of miles away, yes. No, this would not distinguish between the two, but we had already a measurement of the temperature of the atmosphere and its density. And it was not consistent. The depth was not consistent. The atmosphere just couldn't hold it. That's a really good point. And that's the thing about science. You have to always try to figure out, is it this, is it that? And put the evidence known to you together. Just a little bit of bragging. Of course, we've done a little bit with Mars since then. We've actually landed the Spirit and Opportunity rovers by my colleagues Steve Squires, Jim Bell, and others in the department, landed in 2003. And one of them, Opportunity, is still moving around. This is a picture from orbit. It actually shows one of the rovers driving around on Mars by a crater. And the advantage of this is that we're actually able to go places on Mars and find things like this mineral. There are analysis machines on the rovers that could actually tell you what the rocks are made of. This is gypsum. Same thing, it's in the wallboard right here. Gypsum can only be made in the presence of water. It takes that for the chemistry to work out. So here's a confirmation of what we had measured in broad outline at a distance using infrared light. This is what life was like on board those planes. This is a picture from the 1970s. Jim Houck, one of the founders of infrared astronomy, unfortunately just passed away about 5 months ago. Martin Harwood is still doing astronomy at age 86. No, this was the Kuiper Airborne Observatory. This was much, much earlier. It was a C-141 military plane converted, and it had just a small 12-inch telescope. Actually, no, it had a 35-inch telescope, yes. The current one does not. However, Skylab, the first space station, did. Yeah, for a variety. Well, we've now learned that we don't need astronauts to actually operate it. We can just launch the observatory and let it be controlled robotically. Our ability to do robotics was very primitive 40 years ago. And so the astronauts would actually operate it. Now, they had an ultraviolet telescope because ultraviolet also gets absorbed by our atmosphere. If we did not have our atmosphere absorbing ultraviolet, you would get not only a tan, but you would get a bad sunburn in 2 seconds. That's how much ultraviolet is absorbed by the atmosphere. So if you really want to see ultraviolet, you've got to get above the atmosphere. For somewhat different reasons. It's not water, it's ozone. It's absorbing things. We built a telescope at Cornell to test some of the new methods of detecting infrared light. We did a lot of the technology development and actually building tools to record infrared light at Cornell back in the 70s. Just a picture of that telescope. Here are some devices that were built to actually record infrared light in the early days at Cornell. Now, everyone knows about megapixels in cameras, right? It really has been a digital revolution. My phone has a 4 or 6 megapixel camera. I don't even remember. Too many for me to count. We're really very lucky. This is a 2 by 20 pixel camera. 40 pixels, that's 0.00004 megapixels, if I've counted the number of zeros correctly. How am I doing in time, Drew? Okay, I don't know. The professional risk of my discipline is that we enjoy talking about the things that we do. And of course nowadays, just like the instruments in your cameras, we have bigger and bigger and bigger ones to the point where we can now take pictures. Now, they haven't caught up. This is not taking a picture as sharp as your cell phone. But then there are a lot fewer of these made, and therefore there are also a lot fewer research dollars going into these things than there are your cell phones. Everyone here probably has a cell phone. So we're getting better and better all the time. People who do astronomy in other parts of the spectrum also use detectors. Many of them actually work on building better and better ones. So this is a telescope dating from 1984. It was the first telescope launched into space to do infrared astronomy. Completely above the atmosphere. Do you have a question? No. He's doing infrared astronomy. He's measuring the... So this is the first telescope that wouldn't have to worry about flying up on an airplane above the atmosphere for a little while. And Cornell, my team, Cornell played a very significant part on it. Not me. I'm the generation below the ancients. I was an undergraduate at the time that this was being built and launched, but I remember following it with interest in 1983, 1984, knowing that I was going to be an astronomer in a few years. Now, there's several things that one has to do in the infrared. You can see that infrared is produced, my hands are glowing in the infrared. Now, I don't have binoculars here, but imagine you were looking through binoculars, not in visible light, but in infrared. The binoculars are glowing. It would be like looking through binoculars that were 5,000 degrees and were glowing cherry red or white. Could you see anything faint? No, it would be blinded by the light from your own instrument, radiating, because everything radiates, but it radiates according to its temperature. At cold temperatures, it's radiating the infrared. So, what do you think the solution is? Bunch of ice cubes. And as a matter of fact, this had the best ice cube of all. This thing launched with a few hundred liters of liquid helium, the coldest substance that we have as a liquid. As a matter of fact, it never freezes. Helium go all the way down to absolute zero. It's still a liquid. And it boils at 4 degrees above absolute zero. That's 450 degrees below 0 Fahrenheit. So this telescope launched with a big package of refrigeration, liquid helium, and that kept things cold for a year. Then the helium was gone, the telescope warmed up, and it could no longer operate. But it took images of the entire sky. It made the first atlas. Yes? You know, I know that THRM is there, and I know that they did some consulting on the physical design of our 25-inch telescope back in the 1970s. I'm sure we have two mechanical engineers. We're unfortunately losing our instrumental capability at Cornell after decades, and that's a long story in itself. But we use expertise that we need. And so when we're designing new ways of, new tools, new instruments, every instrument has its own challenges, and we go to the people who have the answers, because it takes many, many types of expertise, especially as instruments get more and more complex. Yes? This one did not blow up. I have a picture a little bit later of something that didn't quite work out as it should. Things look different in the infrared. There are a lot of amateur astronomers here. What's this constellation on the left? Would you have recognized it without the guidelines on the right if I'd just shown you that slide? Well, we have a few really good experts here, yes. Well, the thing about space is that there are multiple ways of taking the temperature. It's mostly empty, and it's really hard to measure the temperature of something that's mostly empty. And each of the ways of measuring the temperature measures something very different. So if you were to take the temperature in Earth's orbit, the sun is beating at you on one side, and that's warming things up. And your telescope is radiating heat to space, and that's cooling things down. And the balance is set by those two things. Well, what do you think the average is? The Earth is also in space, and it's cold on one side, and the sun is warm on the other. So if you have the same balance that the Earth has, you have room temperature. So one thing that you do is to build a big shade to put the telescope in the shade. And I'll have a picture that'll show that in just a second. But even though there is very little in the way of gas, but that gas that is around you is fantastically hot. When the astronauts go on a spacewalk, the atoms that are slamming into their spacesuits, there are not very many of them, they have a temperature of about 500,000 degrees. But there's so few of them, it doesn't heat things up. So everything gets complicated. It's part of the fun. But here, the stars, by and large, go away. What you see are the cool clouds of gas and dust. Orion, in particular, the nebula, M78, the Flame Nebula, that's M78, the Flame Nebula over here, these are areas where stars are being born. And they are dark to visible light. A few of them are lit up like the Orion Nebula, but they're not lit up because they themselves are glowing. It's because there are some bright stars nearby that are shining like a searchlight on them. But you don't always find bright stars shining as searchlights. In a few convenient places you do. I'm just going to skip that. We also discovered a few things extra with that spacecraft. At least this is what the press told us we had discovered. We do a lot of things with infrared light, though. This is an instrument that we built at Cornell about 16 years ago that operates on the big Palomar 200-inch telescope, whose mirror was built just a few miles away at Corning. This is a picture of the planet Neptune. And you'll see what appears as a dark spot in visible light that was discovered by the Voyager spacecraft when it went to Neptune is glowing. It has a different temperature. We would not have learned that without taking an infrared view. It's also, it turns out, easier to remove the blurring of the atmosphere. This is what Neptune looks like with a 200-inch, just taking an ordinary snapshot. But this instrument actually has a funhouse mirror that bends its shape about 500 times a second to remove the blurring of the atmosphere. It makes the object stop swimming. Turn it on, and things get a lot sharper. So, back to airborne observatories. This is the Kuiper Airborne Observatory. That's what things look like on the inside. This is it's also the Kuiper Airborne Observatory. And you can see, actually, that was the predecessor to Kuiper. This is the Kuiper. And there's the window that opens. And we now have, it's been 20 years in development, the first astronomy meeting I ever went to in 1988, when I was in grad school. There were posters that said, SOFIA, the Stratospheric Observatory for Infrared Astronomy, beginning operation in 1992. It began operation in 2008. Main problem is getting the money to finish it. We're beggars in astronomy. We rely on people like you to tell our congressman we want more discovery. You're the ones who make it possible for us to do things like this. This is a 747 with a telescope on board, a 100-inch telescope. A telescope that was the largest in the world in 1918 is now flying in a 747. Flies up to 44,000 feet and looks out the side. It's sort of weird because this is based in California, and they have not yet begun operations in the south. They will fly this down to New Zealand to take pictures of the southern sky. But let's say that you launch from California, and you can see the telescope looks out the left side, and you fly west. What part of the sky can you see? South. Good try. What about the north? You have to turn around. So you fly out and you look to the south. You want to look to the east. You fly south. So that's the problem. You have to sort of have a number of targets that are all around the sky, and you make a big circle so that the plane has to ultimately come back to the same landing field. We thought for a while, originally United was going to provide pilots and maintenance for this, and there was even talk at a time that you would get frequent flyer miles. But then someone pointed out, well, it lands at the same place it takes off from. So they give you the miles not on how far you travel, but what the difference is. United's no longer involved, so that's out of the picture. This is what astronomy looks like on board. Instead of having the comfortable passenger cabin, you have lots and lots of computers. The telescope is behind this big blue bulkhead, and the light comes through, and that is an instrument that's on board. As a matter of fact, it's a Cornell built instrument that's sitting there right there. And several people, that guy, that fellow, are Cornell astronomers. That's a picture of the telescope. It's open to the air. Can you believe it? Yes. That was one of the greatest technological challenges in building this, but they solved it. The telescope is on a platform with a whole bunch of servo systems that remove the vibration from the plane. And even the design of the door to make sure that the slipstream would not somehow catch on things, they worked it out, and it works. You don't open it until you get to altitude, where the atmosphere is much reduced, and that makes things a little easier. And you have to shut the door before you get out to the denser atmospheres. If you can't shut the door, then you're not really in trouble, you just have to go really slow. Yes? Yeah. You'll see a picture of Luke in just a second. He's been a friend for 20 years. There's a picture, again, you can see the Cornell logo. On the other side of this blue is cold, low pressure, and on this side is living conditions where the atmospheres can breathe, the astronomers can breathe. So the mission that I have been most attached to, this is a spacecraft that was built by Ball Aerospace and Lockheed, and in 2003 it was launched. This is, I think, that's at Lockheed. That's in the clean room where it was being assembled, and so you can see it's not big, since it's not that much bigger than the humans involved. It's a lot smaller than Hubble. Hubble's the size of a school bus. This is the size of a large SUV. And it is, to date, still the most sensitive infrared telescope that's been launched, especially at the colors that it can see. Other instruments did not do so well. This is one that was actually next to it in an assembly bay at Lockheed. I was actually at Lockheed about a month before this happened. Somebody borrowed the bolts that held the spacecraft to its mounting block. And when they went to tilt the spacecraft, this is a weather satellite. It was. It was a $180 million mistake. So technical people do make mistakes sometimes. But here's the spacecraft loaded in the nose cone of the rocket that sent it up into space, yes? No, this one worked. Otherwise, I wouldn't be here. No, the other one was not, it didn't blow up. It never got to space because it fell over and got crunched while it was still here on the ground. And there we are launching, taking off. I was down with a bunch of my colleagues at Cape Canaveral. That was on August 25th, 2003. And we were prepared to celebrate or to mourn, depending on the way things go. Fortunately, it did not blow up. One of my colleagues, as a matter of fact, had booked 2 weeks of time at a Tibetan monastery. And if things had gone south on the launch pad, he was going to go there and go on for the next 2 weeks to return his sense of mental equanimity. Here's a picture of astronomy at the South Pole. There's a small telescope there. Two of my colleagues have actually spent winters at the South Pole, where you are trapped, cannot get out. If you have some bad medical condition, you simply have to find some way of hanging on until you can be brought out in the spring. The doctor, of all things, back in 1999, figured she self-diagnosed a rapidly growing tumor in her breast. And they were able to they weren't able to operate, they were able to airdrop chemo drugs. So she self-administered chemo, and they operated once she was air-evac'd out about 4 months later. She died 5 years later, unfortunately. There was actually a Russian person at a very small camp, 5-person camp, back in the 1930s, who removed his own appendix. So it's an inhospitable place. But the South Pole, there are a lot of people at the South Pole nowadays, in the summertime at least. It's about 40 people or so in the winter. And anyway, there are some amazing prospects ahead for astronomy. I'm just going to ramp down here. Here is a telescope that people are talking about building 10 or 20 years from now. You can see, by comparison with the pyramids, it's truly enormous. We're in the era right now in which telescopes that are 3 times the size and 10 times the collecting area of the largest that have been working now for the last 30 years are under construction. And these two, the extremely large telescope is one of them, and the 30-meter telescope is the other. Will start operating in just a few years, yes. Because it would be really expensive. We can't even get people back there. And, well, I'll believe it when I see it. They've been talking about that for a long time, too, but they do everything but actually making the money available. This is a design for something called the overwhelmingly large telescope. Until then, we have to worry, we have to make do on the ground. This is a network of telescope dishes that operate just beyond the infrared. It's not quite radio, but it's not quite infrared. It's sort of around where your microwave ovens operate. That is operating down in Chile. I've been to the site, 16,500 feet high, half the atmospheric pressure. You go up there and you start turning blue until you get adapted. And I told you I'd show you a picture of Luke Keller, if Drew is still in the back. I guess he stepped out for a second. I've also had a chance, there's a younger version of me with some of my colleagues. Luke at that time was still at Cornell. And we were deploying weather instruments down in Chile on top of a 17,500-foot peak on this particular climb, trying to find a new place to build a telescope. And we found places, now we're trying to get the money. So there we are. on a location that someone will be developing in the next few years for a telescope. So that's the end of the slides of the talk. I just wanted to show you a very quick animation, and then we can talk as long as people are interested in talking. The thing that I wanted to show you, so here's a picture of something that might look a little bit like a darker version of the Orion Nebula, invisible light. By a darker version, I mean that there are some areas in which the dust is so thick we cannot see the stars in the background. It's a dark nebula. That's what it looks like through an ordinary telescope to our eye, or to photographic film. But now I'm going to fly, but I'm not going to fly through space. I'm going to fly through the spectrum. And I'm going to fly up into the infrared and show you how things look differently. So as I do so, the pink here is from hot hydrogen gas. It emits a characteristic red color. So as I fly to the infrared, this pink is going to turn green, and then it's going to turn blue, and then it's going to disappear because we've flown beyond it. You see the pink? Oops, what's happening here? It is turning green, and now it's turning blue. Pause this. Notice, I'm starting to be able to see through the dark parts of the nebula. Infrared light penetrates this. Yes. But it tells us something. And then as we go even further and further in the infrared, it's now become transparent because we can see all the stars through it. Let me back up to the beginning so you can see the difference. We can't see through it. We can see one star that's sort of hollowed out near the surface. Here it's transparent. And as we fly even further, now we start to see the cold dust emitting itself. Totally different view. It is transparent because we can see the stars behind it, but we can also see the dust glowing with its own emission, even though the dust here is 100 degrees below zero. It's cold. So the universe is cold, lots of it is, and the universe is dusty. And we learn all of that by looking at the infrared. This is how we figure out where things get born, where all the stars have been born over the life history of the universe. That's the primary thing, at least that I think is important because I work on it. Some of my colleagues work in other areas. But it's a new window, every new window. And one thing that we can talk about in the question and answer, we've just opened a new window. What's that? Yeah, totally new window, totally outside the electromagnetic spectrum. Gravity waves. They were detected last week for the first time ever, after decades of effort. I have some graphics as soon as we start talking about this. That ends the formal part of the talk, and I'm willing to sit here and have a conversation with you as long as anyone would like. I'll just leave that on as a background. Thank you very much, everybody. So, my brain is open. Feel free to pick it. Yes? That was 2003 that one fell over. You can't even conceive of how that could happen. Because when you're building spacecraft, everything must have a plan. Removing a bolt, there must be an engineering document that says this bolt will be removed by person X using tool Y, using 15 foot-pounds of torque, and it will be recorded by person Z on form X. Yeah, it's amazing, the degree of detail. But this is one reason why our spacecraft have become so reliable, by having such a profound level of detail. And yet here, my experience as we were building our spacecraft is that I saw a lot of cases in which the way things are supposed to be done was not the way things were actually done. Yes? I will say there is one thing that our group did at Cornell which Lockheed, I mean, it wasn't Lockheed, it was at Ball Aerospace. They hated us for it. But when we negotiated the contract with Ball Aerospace back in the mid-1990s, we said, we want one of our people who has access to the factory floor. We will pay their salary, but they will have a Ball badge, and they will have access to everything. And they report back to us at Cornell. So they were our spy. And Ball hated it. And they have never agreed to that again. But it really saved our bacon a few times. Yes? There is a near-infrared scanner because there is a lot that you can learn about mineralogy from infrared that you can't really learn from visible. So some of the identifications of the types of ices, for instance, came from the near-infrared mapper. And we have a number of people in our department who work in that area. I'm not a planetary person. But well, the point is, these data sets, the way it generally works is that the people who put an enormous amount of time in planning a mission, they have exclusive access, but only for a little while. So in the case of most missions, it's for a year. So you get to reap the rewards as being sort of the first person, but then everybody gets to look at it because other people have to check you. And it's, again, everything's different, but that's the general rule. So sometimes it's a little bit more liberal, sometimes it's a little bit more restrictive, but that's sort of the average thing. Most spacecraft missions have, it's called a proprietary period, because if you spend years preparing for a mission, you want to have a chance to reap some of the rewards, but you can't lock everybody else out, because they're part of it too. And who's going to keep you honest? So we really try to open things up as much as possible. So you, for example, the Hubble Space Telescope has an online archive. You can download every picture that it's ever taken over its lifetime that's more than a year old. And there are some amateur astronomers who do some types of science with that. And of course, we do too. Sometimes you discover a few years later all sorts of things that you could do. Yes, sir?
When the nearest picture captures like this like of a thing apart the head, is that just a scaled down version of that camera right there?
You know, I don't know the technology that's used in there. If it's at a distance, it's probably infrared. If it's from contact, it's probably a thermocouple. But I don't know. I wish I could be a little more concrete on that, but I would hate giving you a wrong answer. I'd rather say that I'm ignorant on that. Yes. I'm sure they were. I'm sure they were. I'm sure they will never work in aerospace again. Let me rotate around. Anyone else back there? Yes. So the successor to Hubble, or I should say a complement to Hubble, is scheduled to launch in 2 years. I keep forgetting it's 2016. And finally, I'm believing that the dates are real. The James Webb Space Telescope will go up, and hopefully will launch for a few years. It's not designed to be able to be serviced in orbit like Hubble was. It's sort of a one-shot, but it's much larger. It's also much more complex. It has 7 mirrors that have to self-assemble in orbit. And if that doesn't work, then it's a $10 billion boondoggle. So we're all going to be crossing our fingers when it launches, that all of this sort of self-assembly origami works. Okay?
In the 70s in the Army to be a photographer,
Mm-hmm.
they told us that there was, and they didn't give us an answer, there was no, like there were for regular film, there were light meters, you got this closer.
Yeah.
But there weren't ones for infrared film. Why weren't there?
Well, it's a matter of actually building devices whose physics allows infrared radiation to respond. We didn't have that until the 1970s, but those required that you cool them down to liquid helium temperatures. So it's only been much more recently that we have consumer-type devices that can record infrared light.
In fact, I learned that we took a pic. One of the ways they found out what the enemy was up to was infrared film, because no matter how much you make it out, it's infrared pattern look like the things around it. You could.
Infrared film can't actually, it doesn't go up to the point where it detects humans, unfortunately, yes. Yes. It's primarily an infrared telescope. So as I said, it complements Hubble. It doesn't replace it. So it does not go as far out as these custom infrared telescopes.
I can interrupt briefly. The still clouds in and out, but we've got the moon available in our 6-inch scope. In our 6-inch scope, I think we've got Jupiter in the 14-inch. We also have the moon in our heliostat. We normally use that to look at the sun, but we can actually, in a nice warm environment, we can actually look at the moon through our heliostat. So you're certainly welcome to stay, but also wanted to make you aware that you have to go to our scope. You can't leave the theater.
Yes, you certainly,
That's the rule.
absolutely, and I encourage you all to do that. I'm going to put up another graphic here. So actually, this work was partially done at Cornell. We have a team that we only learned how to figure out actually what these things looked like in 2005. The computing power and the knowledge of how to code it was not there prior to that. So it's just in time. So talking about gravity waves, this is what two black holes look like when they're merging. And it turns out these are about the same size and mass as what was actually detected a week ago. So this is sped down by a factor of 100. So, yes. So these at the very end are whirling around each other several hundred times a second.
That was proving that Einstein was right.
Yes. Okay. So, trying to figure out how much history to go into. Again, it's a professional risk. So Newton was the first person to figure out basically how gravity worked. He figured that everything pulls on everything else, everything in the universe. It's a universal force of attraction, and his laws stated that the heavier something was, the more it pulled. You double the mass of something, the pull doubles. If the distance doubles, the pull goes down by a factor of 4. So that's Newton's picture of gravity. But Newton assumed that gravity operates instantaneously across space. So if something moves, everything else would feel that change instantaneously. Well, 200 years goes by, and we start characterizing another fundamental force of nature, electricity, magnetism. Electromagnetism, light, is oscillating electrical and magnetic waves, as we now understand. But the laws, as we develop them that describe the behavior of light, tell us that light travels not infinitely fast. It travels very fast, but not infinitely fast. It travels to the moon in just over a second. It's not zero. So if we were to bounce radio waves off the moon, or lasers, which we do, we can measure the distance to the moon now to a 1/16 of an inch by bouncing lasers off of it and timing it. And we know the speed of light that accurately. So light has a speed. So here's this problem. Here's one fundamental force of nature, and our laws say it moves infinitely fast. And here's another fundamental force of nature, and we figured out that it moves at the speed that we can precisely measure. So is it really the case that the fundamental forces travel at different speeds? Or have we just not worked out that gravity actually is a little bit more complicated? So at the same time that people were beginning to puzzle about these things, we started figuring that Newton's laws were not predicting the clockwork of the universe perfectly well. Mercury moves around the sun in an ellipse. All orbits move around the sun in an ellipse. But the ellipse was slowly shifting, just a little bit. It was shifting by, so if the ellipse is oriented this way, here's the sun, and over time it goes around, sort of like a spirograph precessing. It would take millions of years for it to complete that precession. So every year it's a fantastically tiny amount, but it could be measured, and it was measured, and it didn't fit. And we love things in physics when things don't fit because it means that someone's going to make a new discovery. And so Einstein puzzled on this, and he came up with a new law of gravity that predicted almost the same thing as Newton's laws did, but it extended them. And it had two features. Gravity traveled at the speed of light, and the changes would also precisely predict this anomaly in Mercury's orbit. there came yet another prediction out of this. First of all, that exotic things like this could exist, in which space is sort of bent in on itself, sort of a one-way trip. And also, that basically the picture of how gravity worked was different. In Einstein's picture, the presence of mass bends space, and bent space tells matter how to move. So you've seen those little machines at science museums where you put a penny in and it whirls around? But the penny thinks it's moving in a straight line. But because it's in bent space, it makes an orbit. So Einstein's picture was that the planets move around the sun. The planets are moving in straight lines in bent space. And it seems the same, but it makes slight changes in the predictions. And among them, that sheet itself, as the matter bends the sheet of space, and the matter moves, it leaves ripples. Those are gravity ripples. But because gravity is so weak, it's really hard to bend space unless you have fantastically heavy things squeezed into a fantastically small area. If I had a wool sweater here, I would do a demonstration. You know how when you rub like a wool sweater against your hair, static electricity, and if you have a few little pieces of tissue paper, do this when you get home. Take the staticky wool sweater, hold it above the little pieces of tissue paper, they'll come up and they'll be grabbed. They'll lift, they'll levitate off the table. What this tells you is that a few electrons in that wool sweater have overcome the pull of gravity exerted against that tissue paper by the entire Earth. That's telling you how much stronger the electrical attraction is than gravity. The entire Earth has its pull overcome by a few electrons held a little bit away. So gravity is fantastically weak. So it's taken a long time to build instruments capable of measuring those ripples. They were predicted early on. Even Einstein took him a while to figure out that they were real. The equations predicted them, but the equations were complicated, so he thought maybe he made a mistake in interpreting them. And then, no, he convinced himself, yeah, no, they're really waves that come out of this. And then 20 years later, was I really right? And he spent another year working on it with some collaborators. Yeah, I really was right. There are some waves that should come out of this. But he was able to estimate what the intensity of these waves were. The Earth going around the sun leaves these waves. The entire Earth going around the sun emits 200 watts of gravitational radiation. There's just no way that you can measure that. Yes? Mm-hmm. So electrons going around atoms are a changing electromagnetic circumstance, and in certain cases they can emit electromagnetic waves. It turns out atoms don't. If atoms did, quantum mechanics, this was a big problem to be solved, because if atoms did this all the time, the electron would spiral into the nucleus and atoms wouldn't exist, because the radiation of the electromagnetic radiation would lose energy to the atom. So quantum mechanics was a way of reconciling this. But it's exactly the same consideration. Does this happen? In some cases it does. In the case of an electron around an atom, it doesn't. And the answers are subtle. Yes. Yes. The orbits do change, and this is one thing that we look to measure. Now, in the case of the Earth to the Moon, well, first of all, it's not a circular orbit, so it's an ellipse. So even along the orbit, it moves, and it's about 20,000 miles further away from its far point than the near point. So that happens every month. But over long time scales, the Moon's orbit is changing. Some of them are really subtle things that come from Einstein's theory of relativity. And that's one reason that we started measuring these, to have another laboratory, as it were, to look for predictions in which Einstein's theory is slightly different than Newton's theory. And we verified those. We verified them far more with this recent experiment. The other thing is, it turns out that the Moon's orbit is actually growing, which seems a little weird, because if you're losing energy, it would spiral in. So it has to be getting energy from somewhere. Where it's getting that energy from is the rotation of the Earth. So the Earth is slowing down. When the moon raises tides on the Earth, those tides slow the Earth down. So 2 billion years ago, the day was 18 hours, not 24 hours. So over cosmic timescales, the Earth is slowing down. And as it slows down, the tides on the Earth pull at the moon, and they're constantly giving it a little bit more energy and expanding its orbit. So it was formed much closer to the Earth. And as the day is slowed down, the moon has been shifted much further away. That's just left over from when it was formed. So everything, if you have a bunch of matter in motion, gravity makes things lumpier. That's how gravity works. Since it's only an attractive force, it makes lumps lumpier over time. So the early universe was very smooth. Gravity acted on the slight lumps that were in that smoothness, and they grew over time. But as they grew, that means there's motion. So if anytime there's motion of matter against one another, parts of it are swirling. And as things collapse, the swirl is amplified. When a skater pulls in their arms, they spin faster. So every star that's born is born spinning at the limit that it can without flying apart. When stars are born, we see this. We can find young stars, and we can actually measure their speed by breaking the light down and looking at the fingerprints of light. Their edges are spinning at hundreds of kilometers per second. They are these big, distorted ellipsoids. And over time, they slow down. Their magnetic fields interact. They act like tendrils going out into space, and they break, to the point where our own sun spins once every month. But when it was born, it spun once every 6 hours. Good questions, everybody. You're the hardcore crowd. Mm-hmm. 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 Well, I mean, the expansion of the universe is an overall trend. But that doesn't mean that I can't walk closer to you in this room. The universe is expanding, but I can still walk closer to you in this room. So there are anomalous motions in the universe, and also we are part of a bound cluster of galaxies that are all orbiting one another. We're not on escape trajectories. So you can't think of the galaxies within our own local group as flying apart. They are actually orbiting in sort of a complex way.
Supposedly nothing can travel faster than the speed of light, then how do you explain that things in the universe are moving away from each other at a speed that's greater than the speed of
Well,
light?
you can't see something. It's a little bit more complex than that. There certainly can be inferred velocities in the expanding universe itself that would be faster than light, but we can't see